Momentum. So here we go with a one-stop guide to everything you need to know about momentum. So first off, what is momentum? Well, momentum of a body is equal to the mass of that body multiplied by the velocity of that body. Notice it's velocity, not speed, which means this is a vector quantity. So once again, we need to pay attention to the directions in which things are travelling. The really cool thing about momentum is that in the absence of external forces, and everything you do at higher will be in the absence of external forces, the total momentum before a collision equals the total momentum after a collision. And that means that we can use this law of conservation of momentum to find out all about how things collide with each other. So we use it to solve collision problems. There are two types of collision. The first is the elastic collision. And in this kind, the total kinetic energy before the collision equals the total kinetic energy after the collision. In other words, kinetic energy is conserved. The other type of collision is the inelastic collision. Inelastic. And in that, kinetic energy is not conserved. However, that doesn't mean that the total energy is not still conserved, because it is, because that's what the law of conservation of energy says. So total energy is still conserved. So the implication of this is that in an inelastic collision, some of the kinetic energy changes into other forms of energy. For the purposes of higher physics, we'll only be talking about linear momentum, which is a shame because angular momentum is really, really cool, but we had to keep some of the good stuff back for advanced higher. Because we like you, we're going to make life easy and only do one-dimensional, 1D calculations for momentum at higher. And what that means is everything's happening in a line. So if I have a little object there and it's traveling along that way and it hits another little object and then they go off stuck together. See how that's all happening in one line? That's one dimension. We're going to limit it to that for the calculations, which makes life nice and simple. We will, however, briefly mention two-dimensional situations. That's when something like a little block's going along, hits a little box, and what you end up with is the two go off at angles from each other. So one ends up down here, one ends up over here somewhere, and that angle there means we've got a component that away and a component that away, so that's two dimensions. And the reason we'll mention this briefly is it comes up in subatomic section particles. So we'll talk about that when we get to that particle section, but we're not going to do any 2D calculations, only 1D calculations. Now the good news is there are fairly few equations to do with momentum. There is obviously the equation for momentum itself, which is P for momentum, obviously, equals mv. So v is velocity in meters per second, m is mass in kilograms, and p, quite obviously, I mean, what else would you use as a symbol for momentum, is measured in kilograms meters per second. Please, please, please get this right. It's kilograms meters per second. It is not kilograms per meter per second. I've seen that written in exam papers so often and it's just wrong. So please get that right. Now, time for a quick physics joke. Why is it P for linear momentum? Well, that's because we'd already used L for angular momentum. Yeah, that's physics humour. Anyway, more equations. There is a formula called the impulse formula. Now, impulse is another way of saying change in momentum. So with very little algebra, you can demonstrate that the average force exerted on a body multiplied by the time that that average force is exerted is equal to the mass of the body multiplied by its final velocity minus the mass of the body multiplied by its initial velocity. And if you think this is related to the F equals ma formula, you would be correct. So this is the average force, not the force at any one instant in time, but the average force. The time of contact, so the time the two bodies are in contact with each other, like a golf club hitting a golf ball or a hockey stick hitting a hockey puck. That's measured in seconds as usual. M for the mass, in kilograms as always. U, the initial velocity. And V, the final velocity, both of those in meters per second as usual. And this equation comes in very handy for those everyday situations when you want to throw something against a wall and watch it bounce off. There are three more equations which I'm going to detail on the next page, each one for a classic situation in momentum. So first off, we have two objects moving separately from each other. They collide. And then move off separately from each other. So assuming I was given some data about this scenario, the first thing I would do is write down my statement. In the absence of external forces, the total momentum before a collision equals the total momentum after the collision. And then the next thing I would do is draw some little boxes as a little sketch to make sure I know what's going on. Let's call this box A, and let's call this box B. So before the collision, box A is moving with some velocity. Let's call that UA. Box B is moving with some velocity. Let's call that UB. Box A has a mass MA. Box B has a mass MB. Then the collision happens. And according to this description, they continue moving separately after they've collided. So MA hasn't changed as far as we know, but it's after the collision, so it'll be a final velocity, so that's VA. And then box B still has its mass MB and now has a velocity VB. And we can pop that all into one nice equation, which gives us MAV MAUA plus MB UB equals MAVA plus MBVB. So what does this say? It says that the mass of the first object multiplied by its velocity, that's the momentum of the first object, plus the mass of the second object multiplied by its velocity, that's the momentum of the second object. In other words, the total momentum on the left-hand side has to be equal to the final momentum of the first object plus the final momentum of the second object. In other words, the total momentum on the right-hand side. So total momentum before has to equal total momentum afterwards. Now, assuming that I then had values to sub into this equation, I could then solve it for whatever values I didn't have. So far, so good. Second classic example. Starts similarly. Two objects moving separately. From each other. Again, they collide, because if there aren't collisions, then pretty much nothing happens in momentum. They collide. And then move off together. In other words, object A, just as before, with mass A and initial velocity A, plus object B with mass B and initial velocity B, have collided and they've moved off together. In other words, they have stuck together after the collision. Could be like two cars that have had a shunt on the road and one's back fender gets tied up in the front fender of the other and the two cars are stuck together. Could be a whole bunch of things. Point is, they were separate, they've collided, and now they're stuck together. So the mass is going to be MA plus M. Because they're stuck together, so we're going to have a mass that is their two masses combined. And since they're moving together, they're stuck together, we only need one velocity afterwards. That's a final velocity for their combined mass, because they're moving together. So a bit of algebra again. Mass of the first object multiplied by the velocity of the first object gives us the momentum of the first object. Mass of the second object multiplied by the velocity of the second object gives us the momentum of the second object. Add them together, we get the total momentum before the collision, and that would have to be equal to their combined mass, now that they're stuck together after the collision, multiplied by the velocity after the collision. So there is two objects moving separately, they hit each other and they move off separately. Two objects moving separately from each other, they collide with each other, and then they move off together. Now, the third classic example is really the reverse of the second one. We have two objects stuck together. They collide. This is the point where we reveal to you that in physics, the technical term for an explosion is a collision, where the objects move apart from each other. Yes, I know, just roll with it, okay? An explosion is a special type of collision in physics. Just live with it. So two objects stuck together, they collide. I'll put that in quotes just to emphasize it. They collide, and after the collision, they move separately. From each other. So I've got object A, I've got object B, they're stuck together, they're moving with a common velocity u, and their mass in total would be the mass of object A plus the mass of object B. And the collision happens, and after that we have objects A and B moving separately from each other, object A with mass A and velocity A, object B with mass B and velocity B. So again, quick bit of algebra, MA plus MB times their common initial velocity equals MAVA, final momentum of object A, plus MBVB, final momentum of object B. So there we go. Two things stuck together, travelling along, minding their own business. For some reason, they then collide and move separately from each other. In other words, something causes them to explode apart. It could be a spring, it could be a little explosive charge, it could be some magnets, it could be all sorts of things. The point is, they're moving together with a given velocity, and then something happens to make them move separately. So if that's the scenario you're presented with, that's what your algebra should look like. Speaking of explosions, there is a special case of this scenario where the total momentum before the collision is 0, in which case MAVA and MBVB must sum to 0. In other words, left hand side is 0, right hand side must equal 0, which means that momentum there has to be the opposite of that momentum there. So that might be plus something, that'll be minus something, and they'll cancel out back to give you 0. This is the specific case, the specific special case, which is an explosion. Now, at this point, traditionally, we must tell the George Armstrong Custer joke. General George Armstrong Custer, you may or may not have heard of. He's the genius behind the massacre of Little Bighorn. In other words, he got his entire army wiped out. Not the best military candidate ever. Anyway, as apparently sitting in a class at West Point, the US Military Academy, many years ago, and the instructor asked them into how many pieces should a cannonball explode. And bold George, not being the brightest of students, says at least 2. And that is the explanation I'm going to give you as to why we only ever seem to have 2 things in any of these equations. The real, much more sensible answer is we want you to be able to demonstrate that you can do calculations of this type. We don't want to make them insanely difficult for you. A, B there, one common mass, that could be A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, Z, in which case we'd have, for an explosion, still 0 on the left, but we'd have 26 separate terms over here on the right, all needing to be summed back to 0. And that's very unlikely to happen if it's only one-dimensional linear momentum we're considering. Out there in the real world, we'd have things going off at angles, so we'd need to consider 3-dimensional momentum, because it wouldn't just be angles in a plane. Some of the angles would be pointing up the way. And we would also probably need to allow for angular momentum for objects spinning around as they flew apart from each other. So this linear momentum that you're going to be studying this year is a very much simplified version of momentum as a whole. And next year, when we get into the angular momentum, it will be much, much, much cooler because we'll have much more detail in it.